This video will cover Chapter 6 of OCR A Chemistry Foundations in Chemistry. The chapter is The Shapes of Molecules and Intermolecular Forces. We'll be covering all of the following specification points shown on screen. Firstly, we need to go through the electron repulsion theory. Now, this theory basically just covers these 3 points, and these 3 points are all you really need to know. Number one is that electrons repel one another as far as possible. Now, we know that electrons are negatively charged molecules, and so if you have like charges, they'll repel, and this theory suggests that they repel as far as they possibly can. Number two is that lone pairs of electrons repel more strongly than bonded pairs. So, for instance, if we have two atoms, for instance, these are just the shells, and pretend these are the two atoms. If these are a bonded pair of electrons, then these will repel less than if the electrons were just like this. These will repel more, and they'd probably take on more of a spatial arrangement of something like this to be as far away from each other as possible. So number three is that electron pairs surrounding atoms determine its shape. So of course, as electron pairs repel one another, they are what determine the shapes of the atoms. So now we need to know how to represent molecules and what these different symbols mean when you're representing molecules. So this solid line means a bond is on the plane of the paper. Now, you don't need to know these definitions off by heart. The only thing you actually need to know is what these specific symbols represent. So if it's a solid line, it's on the plane of the paper, meaning if this was the paper right here and we were viewing it like this, so this is just the eyes, then it means that it is lying flat on the paper as such. Now, the solid wedge here represents that the bond comes out towards the viewer. So if we're doing it in the same format, this is the piece of paper, here are the eyes, there we go, and this means that this atom is coming out towards us, towards our vision. And the dashed wedge means the exact opposite, so it means it comes out away from the viewer. So because it's the opposite, if we draw it out like this, these are the eyes, then it means that this atom is going the opposite way, away from the viewer's eyes. So, for example, if we have a carbon, and this is methane here, then we can represent it like this. Now, this doesn't really necessarily matter with methane because all of the atoms surrounding methane are the exact same. They're all hydrogens. However, once you get to more stereochemistry, then this is what really matters. So you can see here the general way to draw out these chiral, we say chiral molecules, is A for any one atom, and then up here, B, C, D, and E for each different atoms. So now we need to go through the different shapes of molecules. And as we said before, one of the points of the electron repulsion theory was that the electron pairs surrounding atoms actually determine its shape. So we have these following shapes here of how atoms can actually organize themselves in a compound. So we have linear, where there's a bond angle of 180 degrees, and this is the general formula. The same for trigonal planar, bond angle 120, and then this is the shape. And it continues on tetrahedral 109.5. This is the general shape. Trigonal bipyramidal. This is actually two angles, so it's 90 degrees over here, and over here as well, actually, and then 120 degrees around that. And then octahedral, which is just 90 degrees because there are 6 bonds. Now, the justification, so in an exam style question, what you'll be asked is, what bond angle does so-and-so compound have, and justify your answer. The general form of justifying the answer goes as following. You state how many bond pairs there are, then you state how many lone pairs there are, then you state that bond pairs repel the same amount, and then you say, hence, it has a bond angle of 180 degrees or so on. So same for trigonal planar. Trigonal planar, if we were justifying this bond angle, then we'd say so-and-so compound has 3 bond pairs, no lone pairs, bond pairs repel the same amount, therefore it has a bond angle of 120 degrees. Now, this can get quite tricky when we have lone pairs. So not all compounds have all of their orbitals filled. Some do have lone pairs, and this is what we'll be showing, and these are the only two you actually need to know. So the two are here, pyramidal and non-linear. So we can see here, pyramidal has 1 lone pair and has a bond angle of 107 degrees, and non-linear has 2 lone pairs here, and it has a bond angle of 104.5 degrees. So the justification for this is slightly different, but almost the exact same. You state how many lone pairs it has, then you state how many bond pairs it has, then you state that lone pairs repel stronger than bond pairs, therefore it has a bond angle of 107 degrees or 104.5 degrees. Now, it's important to recognize that this justification, the only things that it differs between is that second and third point of the electron repulsion theory. So we can see here the electron repulsion theory that lone pairs of electrons repel more strongly than bonded pairs, and that electrons repel one another as far as possible. So they differ between the first and the second, sorry, not the second and the third. So now what we can also see is that these two are just a change of this tetrahedral shape here. What I mean by that is every lone pair here that's added is a minus 2.5 degrees from the tetrahedral bond angle. Now, this isn't anything you need to memorize per se, but it's very helpful if you ever forget the bond angles, because then you can just work back from tetrahedral. So what I mean by that is tetrahedral has 109.5 degrees bond angle, and we see it has 4 bond pairs. This one has, pyramidal has 3 bond pairs and 1 lone pair. So if we use the rule that 1 lone pair means minus 2.5, then 109.5 minus 2.5 equals 107. And then if we use that rule further, and that we say that there's a second lone pair here for nonlinear, then it's 107 degrees minus 2.5 again, and that gives you 104.5 as your bond angle for nonlinear. Now, there is a distinction that needs to be made between bond pairs and bond regions. Bonding regions take priority to determine shapes. Now, here is an example. Carbon dioxide has, we can see in both of these structures, carbon dioxide actually has 1, 2, 3, 4 bond pairs. And that's because oxygen donates 2 and the carbon donates 2 to make that bond pair, to make 2 bond pairs. However, this whole compound is still linear. Therefore, it would be represented as such if we were using these symbols. Of course, we know that these are double bonds and therefore we should represent them like that. However, the general rule is that this is linear. It has a bond angle of 180 degrees. Now, why is this if it has 4 bond pairs? This is because bonding regions take priority. So if you were to justify this, then you would state that carbon dioxide has 4 bond pairs, but it has 2 bonding regions. And that bonding regions takes priority, therefore carbon dioxide has a bond angle of 180 degrees. So now we have to move on to electronegativity. Now, the general definition of electronegativity, which you must know, is that it is the ability of an atom to attract the bonding electrons in a covalent bond. Now, an example of this is we can see water. Now, we say here that oxygen is extremely electronegative. This means that when you have the electrons within these bonds between the OH, they tend to lie closer to the oxygen as opposed to the hydrogen. This gives us that delta negative charge on the face of the oxygen, because if the electrons are closer to the oxygen, that of course means that oxygen has more of a negative air, so to speak, around it. Therefore, it is delta negative. And in the same instance, then the hydrogens are delta positive. And that then links back to the first couple chapters where we learned about what hydrogen bonds actually are, and it is the attraction between these 2 delta positive and delta negative charges of 2 different water molecules. Now, it's important to recognize that when you have 2 of the same molecules together, such as H2, this is the same element. Therefore, the electrons lie directly within the middle, and the electronegativity is the exact same, so there is no electronegativity within this compound. Now, for a lot of questions, you'll be required to measure electronegativity, and there are 3 general rules here. So when we're talking about across the periodic table, we state number 1, the nuclear charge. So across the periodic table, the nuclear charge increases. This is because the number of protons within the nuclei increase. Therefore, it is more positive. Now, number 2, across the periodic table, the atomic radii decreases. Therefore, electrons are added to the same shells. Therefore, electronegativity increases. And then lastly, shielding. Across the periodic table, shielding remains constant. Therefore, this is not a factor across the periodic table. Now, if we're going up the periodic table, then this means that shielding, which is the only parameter that actually changes, decreases. Therefore, atomic radii decreases, which means nuclear attraction increases. Therefore, electronegativity increases. So it's important to recognize that when you go across the periodic table to the right, the electronegativity increases. Therefore, if you were going across the periodic table to the left, it would decrease, and all of these factors will just be reversed when you're justifying that. And the same applies for when you're going up the periodic table, electronegativity would of course increase. So when you're going down, it would decrease, and the justifications here would just change. Now we need to talk about bonding. Now there are 3 main types of bonding. There's covalent bonding, polar covalent bonding, and ionic bonding. Now, these values, which aren't actually ranges of values that you need to memorize, but these are the electronegativity values between bonds. And this actually dictates whether that bond is covalent, polar covalent, or ionic. If the electronegativity value is 0, then that means it's covalent. If it's polar covalent, then it's between 0 to 1.8. And if it's ionic, then it is greater than 1.8. Now, you don't need to know these values actually, but it's important to recognize these definitions. So non-polar covalent, which is this one, the bonded electrons are shared equally. Therefore, the bond is non-polar, and this happens usually when the bonded atoms are the same. So like we mentioned earlier, H2, the electrons here are being repulsed or attracted at the exact same amount by both atoms. Therefore, it is non-polar covalent because the electrons lie directly in the middle. The same would go for oxygen here. So oxygen being this double bond, the electrons lie directly in the middle, therefore it is non-polar covalent. Now, polar covalent bonds is when the bonded atoms have different electronegativity values. So this is something very simple like methane. So of course it has these extra hydrogens, but for the sake of simplicity, we won't be referring to them. So the electrons, because carbon, we can see in the periodic table, carbon lies here, which is more to the right on the periodic table. Therefore, it has a much higher electronegativity than hydrogen does. Now, this means that the electrons will tend towards carbon. Now, this is the exact same principle as we mentioned in water. This makes carbon slightly more electronegative and hydrogen slightly more positive. And that's what leads to the delta negative and delta positive charges. It's most easily visualized within water. So when we do have a water molecule, like we mentioned earlier, this is what leads to that strong delta negative and delta positive charges. Now, these are what are called dipoles. Now, all a dipole is the separation of opposite charges across a covalent bond. And that is a definition you must know. Now, here is also an extremely important and quite confusing part that you must be able to understand, is the difference between polar bonds and polar molecules. Now, polar bonds are, as we described above, is when the electronegativity values are large enough to where there's a dipole that's created. Now, single bonds can be polar within a whole molecule that isn't polar. And polar molecules must have permanent dipoles. Now, what is a polar molecule and what does it mean by it having a permanent dipole? Well, we can use water as a very good example for this again. So we can see here that when we do draw out water and the electrons are tending towards the oxygen, this means that the hydrogens are slightly more positive and the oxygens are slightly more negative. And this causes that dipole. And the way we actually represent a dipole is like this. So you can see here, which I'll write out in red so it's more easily visible. That is how you draw out a dipole. Now, to be able to determine whether a molecule is polar, it's whether or not these two dipoles cancel each other out. Now, these two dipoles can't actually cancel each other out because the arrowheads are pointing directly at each other. But if we look at another molecule, such as carbon dioxide, now you can see in the periodic table that oxygen is far more electronegative than carbon. Therefore, the electrons will tend more towards the oxygen, like such. And this means that when we're drawing out these dipoles, the positive charge will start at the carbon and move towards the oxygen. And the same for this one. Now, we can see here that these dipoles cancel each other out. This means that although the bonds of carbon dioxide are polar, the whole molecule of carbon dioxide is not polar because it does not have that permanent dipole. And to have that permanent dipole, the dipoles must not be able to cancel each other out. So this permanent dipole interaction is a type of intermolecular force. Now, these intermolecular forces, the definition is just weak interactions between dipoles of different molecules. That is key here. There are three main types of intermolecular forces. There is an induced dipole-dipole, then there is a permanent dipole-dipole, then there is a hydrogen bond. Now, this list is separated from the weakest at the top to the strongest at the bottom, and that's also important to keep in mind. Now, what is an induced dipole-dipole interaction? Now, this is also known as a London dispersion force or a van der Waals force. So this is weak intermolecular forces that exist between all molecules. And so the best way to be able to describe this is, hypothetically, let's say we have ethane, and we're looking at just the two carbons of ethane here. So if I draw it out as such, and we have two different ethanes here. Now, we did say that the electrons here are in the middle of the compound. However, electrons are always moving around spatially. Remember, they're in shells. So therefore, this means that these electrons are constantly moving back and forth all around one carbon, to the other carbon, to the other carbon, to the other carbon, to the other carbon. And they're continuously doing this sort of figure 8 movement. Now, what this means is that when the electrons are, for instance, on this side of the movement, that means for a very, very, very quick and small instance, this side of the whole molecule is actually delta negative. And that means this side would be delta positive because the electrons lie on the top half. Now, the same exact thing is happening on this molecule of ethane as well. it's moving, and for instance, this side might have the electrons here. So this side is actually delta negative, and this side is delta positive. Well, when you look at that, there are two opposite charges, and these opposite charges are going to attract each other. Now, this attraction is very, very weak because the electrons are, again, constantly moving around, so this won't even happen for that long. Therefore, this is what is known as a induced dipole-dipole interaction. It's induced because the only reason why it's there is because of the movement of those electrons. Now, you don't need to know any of that in detail specifically. The main thing that you need to take away from that is that London dispersion forces or induced dipole-dipole interactions are in every single molecule. They're always between molecules, and they're very, very, very weak. Now, because those LDF dipoles result from interactions of electrons, as we stated earlier and we showed, this means that the strength of LDF is dependent on a couple of the following parameters. Number one is the number of electrons. Now, I don't think I need to explain this, but if there is more electrons, then that means the strength increases. That's quite straightforward. Now, if you were to get this sort of question, this is most likely something to do with melting point or boiling point. And when you're comparing two atoms and one has a higher or lower melting point, or the other has a higher boiling point, then this is how you would, this might be one of the justifications. The other atom has an increased number of electrons, therefore stronger LDF forces, therefore more energy needed to overcome the intermolecular forces. Therefore, it has the higher boiling point or higher melting point, for instance. Now, a very, very important key word here is overcome. You never want to say break because these intermolecular forces don't actually break, they're overcome. Because of this, we can say that helium, which only has 2 electrons, has weaker LDF forces than, for instance, neon, which has 10 electrons, than argon, which has 18 electrons. So this is arranged from the weakest LDFs that it can form to the strongest LDFs. And again, stronger LDFs means higher boiling points or melting points. Now, permanent dipole interactions. Now, we covered this briefly when we were looking at the water molecule. However, the water molecules, again, as we know, forms hydrogen bonds. Now, here, a permanent dipole just means that there is a permanent separation of charges between the two elements. So, for instance, we have hydrogen chloride, HCl here. Chlorine is extremely electronegative in comparison to hydrogen. Therefore, the electrons will sit much more closely to chlorine. That means that there is a delta positive charge on the hydrogen that's always going to be there, and a delta negative charge on the chlorine. Now, the movement of electrons may still happen here because, again, electrons love to move around spatially, but they will only really resonate around the chlorine because of how electronegative that chlorine is, and they want to be around more electronegative elements. Now, it's important to take away from this that this and every single other element still has LDFs. This is important because you'll get exam questions that state what are the intermolecular forces of this molecule. And if you don't put down LDFs, you will lose a mark. Now, if we had already spoken about this, then what are hydrogen bonds? Because they work in a very similar format. Well, simply, a hydrogen bond is just a special type of permanent dipole-dipole interactions, and they only happen in the following compounds. HO, obviously, water, H to N, and H to F. These are the only compounds that actually form hydrogen bonds. And the reason why is because of the amount of electronegativity difference between the hydrogen and the oxygen, the hydrogen and the nitrogen, and the hydrogen and the fluorine. These three are perhaps some of the most electronegative elements on the periodic table. Now, there are a couple anomalous properties of water that we must go through. Now, these are quite simple, and they might have been already explained to many of you that do biology as well. But the first one is that ice is less dense than water. Now, this is very anomalous because if you think about any other solid body within water, it will always sink to the bottom of a big body of water. But when you put ice in a cup, for instance, it always raises to the surface. Now, the reason why this is because hydrogen bonding is extremely conserved in its shape. So we can see here that when you draw out a hydrogen bond, it makes this triangular sort of arrangement here. So we can see all of this dead space between the molecules. Now, as a liquid, the water molecules have enough energy to be able to move around and actually use up some of that free space. But as a solid, it's locked in place, and therefore all of that empty space is actually not usable by the water molecules. They can't flow over each other and fill that empty space. Therefore, it's actually less dense as a solid because of all of that empty space. Now, another anomalous property is simply just that water has a high melting point and boiling point. And that's, again, because of how strong the hydrogen bonding actually is. Hydrogen bonding is the strongest permanent dipole-dipole interaction. Therefore, it has that high melting point and boiling point. Now, an important thing to note here is whenever you're asked to draw a hydrogen bond, you must draw it out as such. So, again, this is really just attention to detail, but the most important part here is how it is completely straight. Now, this is important to be able to represent that sort of dead space that water molecules are able to take up as a liquid and can't take up as a solid. Now, the last specification point for this chapter is simple molecular substances. Now, these are substances that are made up of simple molecules, and that's as tricky as the definition will get. So it's a form of simple, it has a simple molecular lattice structure. This is because it is held in place by weak ion forces, so just LDFs, and that the atoms within each molecule is bonded together via covalent bonds. So there are some key properties of simple molecular substances that you do need to know. Now, simple molecular substances have low melting points and low boiling points, and this is due to their weak ion forces, the LDFs. So therefore, not much energy needed to overcome these forces. Yep. Now, solubility. When you're talking about simple molecular substances, the simple molecular substances can be polar and they can be nonpolar as well. Now, when you have nonpolar simple molecular substances, these are soluble in other non-polar simple molecular substances. Now, the main reason as to why this is because of IM forces. So when you have a nonpolar simple molecular substance, in a nonpolar simple molecular substance, the intermolecular forces break the molecular lattice. Therefore, it dissolves, and that makes it soluble. Now, it's not soluble in polar substances because there's very little intermolecular interactions. And this goes the exact same for polar and polar. Polar and polar are soluble within each other because of the ion forces that can break the molecular lattice again. But if you have polar and non-polar, then it can't break the molecular lattice because there aren't as many intermolecular forces at play. Now, the last property you need to know about is electrical conductivity. And it's fairly simple. There is no electrical conductivity within simple molecular substances. And the reason why is simply because there are no mobile charge carriers. Therefore, it cannot transfer current. Hence, non-conductive. Now, here we have some practice exam paper questions related to the chapter. So, the graph shows the melting points of the elements in period 3 of the periodic table. Phosphorus and chlorine have simple molecular structures. More information about phosphorus and chlorine is given in the table below. So we have the molecular formula of each. So the first question is explain the difference in melting points of phosphorus and chlorine. So when we go to the graph, we can see here that phosphorus is over here. It has a melting point of, I'd say, around 300. And chlorine has a melting point of, I'd say, this line is quite bad. So say maybe 175. So immediately, one of the points that I know are right is that chlorine has a lower melting point than phosphorus. So this question is about melting points, and from what we've covered already, we know that melting points is to do with the a type of intermolecular interaction that is in these molecules. So knowing that, I can immediately start off by saying which type of intermolecular interactions these actually have. And I know that chlorine and phosphorus have induced dipole interactions. And the reason why I know that is because these are the exact same elements. Therefore, if I'm drawing out chlorine, it's going to be in the middle. Therefore, it won't have any delta negative or delta positives that are permanent. Therefore, it can only be induced. Now, I also can see from this table here that phosphorus exists as P4, whereas chlorine exists as CO2. Therefore, I can tell that phosphorus will have more electrons. Now, I can also back this up by looking at the periodic table as well. But from the molecular formula, we can immediately see that phosphorus will have more electrons. So I can point that out too. So I've just put in my observation there. Phosphorus exists as P4, whereas chlorine exists as Cl2. Therefore, P4 has a higher number of electrons, which means stronger LDFs, therefore a higher melting point. But I also want to add my key phrase. That means that there's greater energy required to overcome phosphorus LDF forces. And therefore, I'm confident this will get 3 marks, because even if this description doesn't have any marks, which it probably doesn't because it's an explain question, I can be confident that these 3 points will. And that's everything you need to know for OCR A Chemistry's Chapter 6, Shapes of Molecules and Intermolecular Forces. Thank you very much for watching, and I hope you've learned something.